Let's see one example how to apply this method. In this example, you can see one simple supported beam. It is subjected to two types of loading. One is point load, another one is uniformly distributed load. For this beam, you have to calculate the reaction first. Number two, you have to draw the bending moment diagram by parts, then determine the moment, slope, and deflection equations. Then you have to find out the deflection at mid-span of the beam. You can see in this beam, if we take this section, we can write one moment expression here. Then if we take another section here, you can write the distance will be x, the moment expression you can write there. If you take another section here, you can write one moment expression for this section. So you have three moment expression. From these three moment expression, if you calculate d square y divided by dx square equals to m, using this formula, you can write three moment curvature relationship. Then by double integrating, you can calculate the equation of the elastic curve for this beam. It will give you lengthy calculation. Instead of that, you can write one moment expression considering one section towards the end of the beam. That means if we take one section here only, then we can write the moment expression using singularity function. Then it will represent the moment expression for this section, moment expression for this section, and moment expression for this section. Let's see how we can do that one. So this is your beam. We'll take one section here at any distance x. Now, if we want to draw bending moment diagram by parts, you can see we have three load. This is 9.75 kip. This is the reaction. This is 1 point load, and this is the distribution load. To draw bending moment diagram by parts, what we'll do, we'll take out this section and we will consider fixed supported here. The fixed support will be along this red line. Then you can draw one by one. First, for this reaction, if we want to draw the bending moment diagram, what will be the bending moment diagram? This will be the bending moment diagram. As you know, for point load, the bending moment diagram will be the linear line. And what will be the ordinate of this? If it is 9.75 and it is x, this ordinate will be 9.75 multiplied by x. And this is positive bending moment as the load is upward. Next, we have to draw the bending moment diagram for this 10 kip load. It will start from here and it is a downward, so negative moment will come. So 10 multiplied by, here the distance will be x minus 3. The total distance is x and this is 3. So this distance will be x minus 3 and this will be your bending moment diagram. And what will be this ordinate? Is 10 multiplied by x minus 3. So this will be your ordinate and this is negative moment. Finally, we have this 1.5 kip per feet as we have fixed here. So we have to take only this portion and this load start from here. So we'll start from here. And this is uniformly distributed load. As you know, for uniformly distributed load, the moment diagram will be second degree curve. It will be like this. This distance is x minus 6. So this ordinate will be w x minus 6 whole square divided by 2. W is 1.5. So your moment expression will be 1.5 multiplied by x minus 6 whole square divided by 2. This is in fact the moment diagram by parts. When you draw this moment diagram by parts, if you put the x value directly at the end of this beam, you can get the moment diagram by parts. It is 9.75 multiplied by 12 will give you 117 feet. This one you can draw here because it is downward. You can draw in separate figure also. 10 multiplied by, just put the x value. It is here 9. So 10 multiplied by 9, this is 90, and this is minus 27 keep feet. This is your moment diagram by parts you can draw. Now, what you will do, you have to write the moment expression. Moment expression is very easy. You can see the previous file. This plus, this minus, this minus. If you add these three together, this is the moment expression. So this is positive, this is negative, this is negative. So this minus this will be your moment expression. So if you see your moment expression, this is positive one, this is negative one, and this is negative one. When we'll write this moment expression, we'll write it using pointed bracket. This pointed bracket means for this section only the first term will be valid. For this next section, these two terms will be there, third term will not be there. If you take this section, this is the total moment expression. So this generally expression, then this EI multiplied by d square y divided by dx square equals to m. So write this expression, EI d square y divided by dx square equals to m. This is the value, moment expression. Now integrate one time, you will get slope expression. You integrate one time, this is 9.75 x square divided by 2. This way you can write, just here add 1 divided by 2. Here it is plus 1, so it will be 3 divided by 3 multiplied by 2, it is 6, and one constant of integration will come. This will give you slope equation, but we have to calculate C1. Later we'll see how to calculate C1. Then if you integrate again this expression, you'll get, this is the equation of the elastic curve, C1x plus C2. We have, in this equation, we have two constant of integration, C1 and C2. So we need two boundary condition to solve these two constant of integration. So what is the boundary condition? We are measuring x from here, from the left support. At x equals to 0, deflection is 0. Similarly, at x equals to 12, deflection is 0. So our two boundary condition is this. At x equals to 0, y equals to 0. At x equals to 12, y equals to 0. Now, if you apply this boundary condition, you can give the name. This is equation 1 and equation 2. So if we apply this boundary condition one by one, you can see at x equals to 0, y equals to 0. From equation 2, we will get C2 equals to 0. That means constant of integration C2 equals to 0. At x equals to 12, y equals to 0. From equation 2, if you put y 0 and x equals to 12, you can find C1, and C1 will get minus 126 feet square. Please note the unit here. Once you have C1 and C2, you can find the equation of the elastic curve is this. This is your equation of the elastic curve, and you can find also the equation of the slope. So this is your equation. Just put back C1 and C2 in equation number 2. You will get the equation of the elastic curve. From this equation of the elastic curve, you can calculate deflection at any point along the length of the beam. In our question, we need to find the deflection at mid-span. So at mid-span, you can write x equals to 6 feet. Instead of x, if you put 6 feet here, then you can calculate the deflection. And this deflection at the mid-span equals to minus 450 divided by EI, if feet cube. This complete your first example.